Am I audible?
Yes, ma'am, you are audible. Good morning, ma'am.
When I be a mini WhatsApp group, ask your friends to join the meeting. We'll wait for 1 or 2 minutes and we'll start the session. What we have seen in the previous class, ma? Which topic we have discussed in the previous class? Do you remember that? So we were discussing regarding the VLAN, trunking and tagging, right? It is 8 no, IEEE 802.1Q. What is the purpose of that frame? So tunnel, those things we have discussed in the previous class, right? So in today's class, we'll be seeing the PGP. So that I'll share my screen. Is my screen visible?
Yes, ma'am.
So in today's class, we'll be seeing PGP, okay? The terminology, concepts, operations, how to implement the basic PGP together with attributes, path selection process and all, okay? Most probably we'll be completing till that. In the upcoming classes, we'll be seeing controlling PGP routing updates and all, fine? So we'll start with what is PGP? So PGP, it is a protocol, okay? So PGP, it is nothing but a broader gateway protocol. Okay. So it is a routing protocol, which is used to exchange the routing information between the autonomous systems, especially on the internet. Okay. So it we'll be classifying the routing into two types, right? So inter-domain routing and intra-domain routing. So it comes under inter-domain routing. Okay. So sharing the routing updates in the interdomain routing. Okay, so it will be connecting. So within the autonomous systems, it is called as intra-domain routing. So from autonomous systems to another autonomous systems, it is called as interdomain routing. So PGP is used to share the routing updates between the autonomous systems, that is interdomain routing. Okay, so how to share the ensure the routing is loop free. Okay, for that it will be supporting policy based routing. Okay, so the main purpose is to provide the communication between multiple autonomous systems. Okay, so here the autonomous systems are numbered from, so see here, 64520, 65250, 6550 and 65000. These are the autonomous numbers. We have multiple autonomous systems. So four autonomous systems which are numbered, right? And we have six routers: R2, R3, R1, R2, R3, R4, R5, R6. Okay. So these will be acting as PGP speakers. Okay. So which will be responsible for advertising the routing information and also receiving the routes from one system, from one router to another router. So first you need to understand what is autonomous systems. So autonomous systems is nothing but a group of networks or even a multiple devices will be having control. A single administrator will be controlling that. Okay, so it will be following the same routing policy. So multiple, even the multiple networks can be combined here. Okay, which will be following a same routing policy. So that is called as an autonomous system. So each and every autonomous system will be having a unique number that is called as an autonomous number. So here four autonomous systems are there which are numbered as these are the numbers. Okay, so they have six routers connecting. In this example, 65000 is having R2 and R3. Likewise, 65250 is also having two routers, R4 and R5. Okay, so the direct PGP connection will be between routers in different autonomous systems. Okay, so that is called as EPGP, exterior, that is external PGP session. Okay, so R1 and R2, these two will be connected with the help of EPGP connection. Okay, so inter-domain routing that happens with the help of IPGP, that is internal PGP. Fine. So the route updates advertisements. Each router will be responsible for advertising the network. Okay. So which are the networks are there? Okay. So which are the networks owned by this autonomous system that will be updated to another PGP neighbor. So update message will be having AS path information. So list of autonomous systems that are that the route. If I want to pass to R6, how many autonomous systems? The entire path will be provided. Okay, so the path selection, the best path will be in PGP, it will be selecting the best path. So best path will be selected based upon the policies and path attributes. Okay, not only will not consider the shortest path, rather policies will be taken care and also path attributes will be taken into consideration for selecting the best path. Okay, so AS path will be helping to avoid the loops. Okay, loop prevention. If the router sees its own autonomous number in the AS path, in that case, it will be just rejecting the route. In this way, it will be avoiding the loop prevention. Fine. So the role of PGP is to provide both the connections, that is external PGP connection and internal PGP connection. So what is external PGP connection? Multiple routers which are running on different autonomous systems. If you want to connect that, I'll be going for external PGP connections. And internal PGP connections will be used within the autonomous systems. Right? So here, if I want to share the information between R2 and R3. So R2 and R3, it is within this particular autonomous system. For that, we'll be using IPGP. So R1 and R2, we'll be using EPGP. Fine. Any doubts? Any doubts in the introduction part, Kana? Any doubts?
No, ma'am.
So if you have any doubts, please stop me then and there and you can ask questions. Fine. So now we'll see the path vector characteristics. So the path vector is nothing but it refers to the sequence of autonomous numbers. Okay. So in the routing update, we'll be having a sequence of numbers. right? Autonomous systems. So that represents the entire path, the routing, uh, how the routing should happen. So how to reach the destination. So that will be provided by hop by hop autonomous number will be provided. So that from this you have to move on to this particular autonomous system. Then you have to reach to this autonomous system to reach the destination. So this sequence will be stored inside AS path attribute. Okay, so each AS will have the path, and when it goes out, it will be adding its own AS number, AS and unique number to the AS path list. Okay, so before updating the path, before the packet moves on, it will be updating that. Okay, so this example, AS64700. It contains three networks. So what are the three networks? 192.168.24.0, 25.0, 172.20.0.0. Okay. So when it advertises these networks to, this is actually 64600. It is another autonomous system, right? So when it updates or when it advertises these networks, it will be adding its own AS number to the path attribute. So what will be the path? The path will be okay 64700. So this information will be copied in the path. So when this autonomous system, if it sends any updates to 64520, if it wants to advertise all the information, so whatever it is holding, in the path information, so it will be adding its own number 64770 hyphen 64600. Fine. It will be appending its own number. Fine. Then if it moves on to the next autonomous system, it will be adding its own number. Fine. This is how the path update will happen. Okay. So the purpose of AS attribute is nothing but it will be providing routing information. Okay. So and also it will also provide the loop prevention. Okay. The router will not accept a route which is already passed through its own autonomous system. Okay, why? Because in the path information, the routing ID will be there. So if the ID is already there, it will be preventing that. It will avoid that. Okay, it will just ignore that. Okay, so the path selection criteria will based upon the shorter AS path. Okay, that will, yes, ma'am. Anyone wants to say something? Any doubts? So this is actually the AS path. Fine. So AS path, it is actually a routing policy. It supports policy-based routing. Okay, so yes level policy-based routing will be adopted. So PGP always follows the routing policy decisions. Okay, it will be based upon autonomous sequence numbers. Okay, autonomous systems unique numbers in the AS path. Okay, so these policies will try to help how the traffic, which are the packets are entering, which are the packet are leaving, which are passing through an autonomous system. So all the informations, the how the data will flow, everything will be stored. Say for example, if an ISP, if it has been configured a policy to prefer a certain path for outgoing traffic, okay, in that case, or to avoid a certain autonomous systems for the security or performance reasons, I'll be adding the policy details. Okay, so policies, it will be using attributes from the routing information. So the sequence of the autonomous numbers, autonomous systems unique number, the route, from the AS path itself, I can find the sequence of autonomous systems where the packets has to pass through to reach the destination. Okay, and also the local preference will be there. So it will be indicating preferred exit points from the autonomous systems. So if multiple routers are there, and multi-exit discriminators also will be provided. So it will be suggesting certain entry point at in the autonomous systems. Okay, and also it provides the origin, next hop, and communities for the fine-grained control. Right. Together with that, these policies will be set on the routers. Okay, so all these things will be controlled by the administrators. Right. So the route advertisements will be there is a advertisement rules. So advertisement rules will be provided. So say for example, a rule, a PGP router can advertise to its external peers, only neighboring in a different autonomous systems, only the routers it is currently using. Okay, so what is the purpose of this rule? So this rule will ensure consistency. Okay, so the routers can tell the neighbors about the valid together with the reachable routes, right? And also it is a trustable route. So it will be reducing the risk, right? And also hop by how routing paradigm will be provided. So routing decisions will be made on hop by hop. So each yes autonomous system will be deciding the next hop. Okay, so if I want one autonomous system will be taking a next hop as a another router. Some other will be taking another way. Yeah, the backend will be handled independently. Okay, based on the own routing table. Okay, own routing table together with the own policies. Right. So the PGP it will enforce not by dictating the entire end-to-end path. So it will be independently chosen by the routers. Okay. So some routing goals cannot be achieved because each autonomous systems they have only control its own the own segment, right? So one autonomous system cannot tell the neighbors that is sending this traffic through a different route you normally use for your own traffic. I cannot instruct it. Okay, the neighbors will apply its own policies, ignoring such a sort of results, request and all. Okay, so the PGP policy will reflect the commercial relationship. Okay, so preferring the customers will be choosing the parts. Okay, customer routes over the peer routes. So it will be providing the security together with traffic engineering can be administered in a very proper way. Right? So path vector characteristics, multiple possible path will have, right? So in this example, from 64520, if I want to pass to 64700, I have two paths, right? This is ETA. This is path one. I can reach from this way, and this is path two. Right? So two parts, multiple parts are available. So what is the part one? 64520, 64600, 64700. That is one path. Another path is 64520, 64600, 64540, 64550. Another system, autonomous system is there, which is not shown here. 64550. From here, it is connected to this. Okay, so multiple path exist, right? So these are different route possibilities based upon the network topology. So even there are multiple paths exist inside the network, the PGP will not advertise all of them to the external neighbors, right? So only the best path will be advertised. Okay, so 64520 autonomous system, it will be selecting the best path to reach 64770. Okay, so this will be depending upon the decision, PGP decision rules. Okay, so highest, it can be based upon the shortest EAS path or highest local preference or the lowest origin type. Okay, lowest MED value or EGP, ePGP over IPGP can be preferred. Okay, or else the lowest cost can be preferred. Fine. So in this example, they've taken 64520. From here, it is moved from 64600 and then to this. So this path is preferred. Say for example, number of costs based upon the shortest yes path. The path might have been chosen. Okay. So like interior gateway protocols, PGP, it will be advertising only the best path. This path alone will be advertised. Okay. So even multiple path exists, this path alone will be exist. Fine. Sorry, it will be advertised. So it will be reducing the routing table size. Unnecessary routing advertisements need not to be provided, right? Multiple, if I provide all these things, it will increases the performance. Sorry, it reduces the performance, right? And we keep on sending the information. So unnecessary route advertisements can be minimized, right? So even it simplifies the route selection for downstream autonomous systems, right? So if this wants to select the path directly, it can directly pass to this or even 64512 instead of moving multiple paths. So if it is advertising this information to 64512, it will be directly passing the information. If it wants to send the packets to 64700, directly it will be sending the path in packet to this autonomous system so that it will be reaching 64700. Okay, that is the advantage. The next one, multiple entry points, 264700. As we seen, this is the source point. Okay, I'll take this one as the source. Okay, so it needs to reach to the destination. We'll take this one as the destination. 64700 is the destination. So what is the part one? Part one from 64520, 64600, and 64700. This is actually part one. There is a part two as well. So part two, 530 from 540, 550, and it can reach the destination. Okay. So destination network, it is in 64700. Okay. So these are the networks connected and they follow the same policies, protocols. So all these things are grouped under a single autonomous system that is which is numbered as 64700. So each autonomous system will be deciding the next hop, okay, in order to send the traffic, not the full end-to-end path. So in this example, A64512, what it will do, it will does not dictate how other autonomous systems they want to they have to forward the packet after it leaves from this particular network. Okay, so what it will do, each autonomous system, it will just send the path. What is the shortest path? Six. In order to connect to these two six systems, either it will be sending the packet to this autonomous system or to this autonomous system, right? So each autonomous system, it will be running its own policies, routing policies, in order to forward the traffic. So when it reaches 64520, it is need not to take this path or to take, we cannot instruct. 64512 cannot instruct you need to take this path or this path to reach the destination. So 64520, it will decide in which way it has to. It can even take this path to reach the destination. Fine. So uh, it uses this source will use its own local policies to select the best path. So when it reaches to 6, if it's selecting 520 as the best path, it will be sent, and 520 will be deciding whether it has to pass the packet to 600 or 540. Okay, so it can be influenced by local preference settings or other PGP attributes. Okay, so at last it will receive by the destination. In this example, 64520 will advertise its path to 64700. So 530, 540, all these things also will be advertising the informations to 6400. So when a system, some system which is part of this autonomous system wants to send information, it will be receiving the advertisements from both the autonomous systems 64520 as well as 64530. Okay, so it will be deciding, it will choose the path to forward to which way the packets has to be forwarded. The receiving side, it can receive the packets from both the ends, but forwarding side, it will be deciding. So in which way it has to forward the packets. Fine. Any doubts? Any doubts, Ma? What about others? Out of 60 plus students, I'm getting always only one response. Now we'll see the path PGP characteristics. So PGP, it is called as a path vector protocol. Okay, advanced distance vector protocol or a path vector protocol. So advanced distance vector protocol, it is PGP. It is actually a path vector protocol. Okay, so instead of advertising the distance to the destination, the PGP will be advertising the AS path. Okay, the full AS path, the sequence of AS numbers that the route is taking. Okay, it also includes additional attributes. So, what is the local preference? What is the MED, multiple exist uh, MED value? All these informations will be there. And the AS path itself, multi-entry points, all these informations will be there in the packet itself, right? In the AS path itself. And also it uses TCP protocol. TCP, it is used for the transport. Okay, so PGP will be running on the top of TCP. So the what is the port number for PGP? The port number is 179. So it will be a connection oriented protocol. Why? Because it runs on the top of TCP. Okay. So the connection oriented sessions will be provided between the PGP peers. Okay, for reliable delivery, it uses acknowledgements, retransmissions, flow controls. Everything will be handled by TCP. Okay, so because TCP already ensures error recovery and transmission, the PGP, it does not need mechanisms like sequence numbers, okay, for recovery, routing policies, path selections. It concentrates only on those things. Okay, so the TCP connection is established between PGP peers, right? So the PGP messages will be exchanged in the form of TCP segments. So out of order, corrupted packets, everything will be handled by TCP, not by PGP. So PGP will be maintaining the routing table, that's it. And it will be sending only the updates. When there is any changes occurring, it will be sending the updates. That's it. Now we'll see PGP packet. So frame level packet, it is a layer 2 packet, that is a data link layer. That is frame, right? It starts with the frame header together with source address and the destination address, MAC addresses. So since it is a frame, it will have only the MAC address, only the packet will have IP address, right? And it also includes cyclic redundancy check for error detection. Okay, so CRC is used at layer 2, data link layer. Together with that, you have an IP packet. So the what will be the payload? Payload will have IP packet which will be placed inside the payload, right? So you will have IP header which will be containing the source and destination IP addresses together with the protocol number, TTL. Okay, so all those things will be set, and it will the port number will be set to 6 in order to indicate that is a TCP protocol. Sorry, TCP packet. Fine. The TCP will be managing all the reliable delivery, sequencing, acknowledgements, everything. And you have a port number. So port number will be identifying the applications. So what is the port number for PGP? It is 179. So for Telnet, it is 23. SMTP, it is 25. In the previous slide itself, I've told you for PGP, it is 179. So together with that, you have PGP data. So that will be placed inside segment payload. So it contains the PGP messages. Right? So there are 4 types of message: open, update, keep alive, notification. All those information will be here. Okay. Now we'll see. So who are the speakers and who are the peers? So PGP, it consists of speakers and peers. Fine, PGP speakers, the routers which are running PGP, they are called as speakers. Peers are nothing but the neighbors. So the two routers uh, who wants to establish a TCP session with each other for exchanging the routing information. Those two things are called as peers. Okay, so what number they'll be using? Once the port number 179 for the communication. Okay, so before exchanging any data, they want to have a three-way handshaking mechanism. Why? Because it is a TCP connection. Okay, so the PGP speaker must establish a three-way handshaking mechanism. Okay, for exchanging open message. Okay, for that itself, or even to confirm the session with keep alive messages, they want to create a three-way handshaking mechanism. So once the session is established, the routing information will be exchanged between the peers. Okay, so the PGP will be sending only the incremental updates. So changes, whatever the changes. So instead of sending the entire routing table, only the changes will be sent. Okay, so it will be minimizing the bandwidth and also the processing power. Okay, so PGP and it will not send any periodic updates. Periodic full routing table updates will not be there. So it relies only on triggered updates. So send only when there is a change in routing information. So periodic updates will not be there. So it also send keep alive messages. So which is used to maintain the TCP session and also to verify the peer availability. Fine. So now we'll see the tables. So it stores all the PGP peers. So what is PGP peers? The neighbors. Okay. So the routing information will have the neighboring IP address, the state of the session, whether it is a idle state, whether it is a connected state, active state. Okay. So open confirm state. There are different states. Okay. So it maintains the three informations: the neighboring IP address, what is the neighbor's IP address, what is the session state. Okay, together with that, it will be having the PGP version and yes number. Right? So this is the routing information, routing table. So this table is the table contain all these informations. This table is used to track who are the neighboring routers. Okay, so PGP table contains all the PGP routers. So all the PGP routers in there, in the sense, the neighbors will be learning from the nearby neighbors, right? From wherever the routes are being advertised, they'll be learning from its own neighbors. All the informations will be there in the PGP table. It is not same as the IP routing table. So multiple possible routes to the same destination can be provided. So routes which are not currently installed in IP routing table, because only the best path is chosen in the forwarding decision. But here, it will have the entire, all the advertised informations will be there. So IP routing table, the main routing table is used to forward the packets. Okay, it will be receiving the best track from the PGP table. So it will contain the routes from PGP, static routes, IGPs, okay, connected networks. All the information will be taken by the IP routing table. Fine. So from that, PGP will be taking the best route and the PGP routing will be taken. So interactions between the tables, you have IGP routing table, which will be updating. So see here, IGP is responsible for updating the IP routing table directly. And PGP routing table, the PGP routing protocol will maintain the PGP table. So it will be sending only the best routes to the IP routing table. So the routes from IP routing table, it can be redistributed into PGP. So they can advertise to the other PGP peers. So these informations can be shared between IP routing table together with the PGP table. Fine. So PGP table, it is independent table. Okay, so from the router's IP routing table, it is an independent table. It will store all the PGP learned routes. Okay, it may include multiple possible routes to the same destination. That doesn't care, but it will store all the PGP learned routes. So the routers will be selecting the best path based upon the PGP path selection process. So only the best routers will be offered from the PGP table to the IP routing table. Just now I've told you. So information will be shared between both the tables, PGP table and as well as the IP routing table. The route redistribution, if it is required, that can be shared. So routing process, PGP does not automatically discover the neighbors. Okay, so periodic updates will not be there. Only the trigger updates will be there. Likewise, it will not automatically discover the neighbors. Each neighbor, they have to explicitly configure. Okay, so once it is configured, the PGP will be establishing a TCP connection, TCP session. So on the port number 179. Okay, so with all the neighboring peers, with each of its neighbors, the connection will be maintained with the help of PGP, TCP, keep alive messages. Right? So this connection will be maintained, and also once it is established, the neighbors will start to share the best PGP routes. It will share only the best PGP routes. So these routers, what they'll do is they'll be collecting those informations into PGP table. So whatever the informations that are being collected, it will form a table. So each learned path will have an PGP attribute. So each PGP attribute, just now I've told you, what are the things that will be there in the PGP attribute? What is the local preference? What is the ACE number? What is the ACE path, MED value? All those things will be there in the PGP attributes. Okay, so the PGP will be applying the route selection. So the route selection process will be choosing only a single route. Single route best path will be chosen from the network. Okay, so the best route will be offered to the IP routing table. Fine. So the redistribution even can be used to share the routes between PGP and other routing protocols whenever it is required. Fine. So the neighbor configuration, PGP, just now I've told you, it will not discover the neighbors automatically. So each neighbor, they have to configure explicitly. So PGP will be forming a TCP connection, right? So on the port number 179. So with the help of PGP, TCP, keep alive messages. Then PGP routes will be selected. That will be updated in the table. Only the best path will be given to the IP routing table. If there is an configuration is required, redistribution is required, in that case, the IPT routing table and PGP routing table, they will be sharing the information. Okay, so the routes will be compared and only the best path will be updated inside the IP table. So the router, in that case, you have the administrative distance. So administrative distance, you have external PGP routes and also internal PGP routes. So administrative distance for, if I'm taking the external PGP, administrative distance can be for 20. And for internal PGP, the administrative distance can be 200. So only the route with the lowest AD will be installed in the IP routing table. Right? So even if there is a best path, best route, the best route will not be installed in the IP routing table. Why? Because based upon the IP administrative distance, administrative distance, whichever is having the lowest one. So in this case, if the external PGP is having the lowest one, then it will be updated. So in this case, if an internal PGP update is administrative distance is low, the external PGP information will not be added to the IP, right? IP routing table. That is very, very important that you have to remember. Fine. Any doubts as of now? Any doubts, ma? Any doubts? Are you there in the meeting, ma? Do you have any doubts? Aditya, Ajay. So explicitly, I want to call your names to get the answer for each and every question, right? For asking itself, Arjun left the meeting. Fine, very good. I've given credentials to unmute, or else you can use the chat box to respond. So now we'll see PGP messages. So message types. What are the PGP message types? So four main types of messages are there. One is open, keep alive, update, and notification. So open, which will be sent between two PGP peers for establishing a TCP connection. Fine. And keep alive, it will be sent periodically to maintain the connection. So this for establishes the connection, to establish the connection, to maintain the connection. Right? Update is used to advertise the new rules. And notification for sending any error if it is detected. Okay. So open for to establish the connection, keep alive to maintain the connection, update for sending the new routes, and notifications for sending if the error, any of the error is just detected. Okay. So now we'll see each and everything in detail. First we'll see open and then we'll see keep alive messages. So TCP session initiation can be done with the help of open message. Okay, the PGP will be establishing a TCP connection, right? TCP connection between the two peers on the port number 179. So the first PGP message will be sent only after the TCP connection is established. Okay, so open message will have the informations like PGP version, okay, what is the AS number, what is the hold time, right? All these informations will be there in the open message, right? So even it can include the optional parameters as well, right? So once the TCP connection is established, once after the open message, TCP connection is established, then we have to maintain the connection. So if the open message is accepted, the peers will be sending a keep alive message. So keep alive message to confirm the connection. So once both the sides confirm, the PGP session will be established. So at the session startup, the peers will be exchanging the PGP routing information. So PGP routing information, it will have the routing tables, right? And after that, they'll be sending only the incremental updates. So incremental updates, they'll not be sent on the periodic basis. If there is any changes occurring, in that case only they'll be sending the updates. And so the keep alive packets will be sent to ensure the connection. Okay. So the notifications will be sent for checking if the error is detected. In that case, notification messages will be shared. Fine. So the incremental updates, it will be sent one if there is any changes. When the changes is occurring, it will not send any periodic updates. So which will be the periodic update? Periodically, they'll be sending in order to ensure the connection. They'll be periodically sending a keep alive messages. So the keep alive messages like hello packets will be shared in the IGP, right? So in the same way, keep alive packets will be shared in order to confirm the PGP connection is still alive. Fine. Now we'll see open message. So open message, it is the first PGP message which will be sent after the TCP three-way handshaking mechanism, right? So it will include a version. Version is a 8-bit field. Okay, so which will be indicating the protocol version. So PGP version. Okay, so in this example, it is PGP 6. The next one, it will have the autonomous system number. So autonomous system number will be represented as a 16-bit field, which is a unique value, which will be verifying the number against with the expected value. Right. So if the autonomous number if in case it is incorrect, the PGP session will be terminated. The next one is hold time. This is also a 16-bit value. The maximum number of seconds it can hold. Okay. So that will be shared. So if this time elapses, what will happen? The session will be terminated or session will be dropped. And the next one, PGP router identifier, the router ID. It is a 32-bit field. It is almost like a unique PGP identifier. Okay, that is nothing but an IP address. Okay, IP address will have a 32 bits value, right? And it can include optional parameters, the length, type length value, okay, session authentications, the security informations, all those things can be included in the optional parameter. So these are the informations will be there in the open message. Now we'll see update message. So update message, which is used to advertise the new rules, right? And also it is not periodically will be sent. If there is any changes, only the information will update message will be sent. So one message will have only one path. So if multiple messages need to be advertised, multiple update messages are sent. Fine. So one update message will have only one path. So all the attributes in the message will be applied to the single path. That's it. So the networks, whatever the networks listed are those reachable via that path. Fine. So fields in the update messages are withdrawn routes. So whatever the IP addresses, prefixes for the routes being removed from the service, that will be placed. So if no routes are withdrawn, the field will be empty in that case. Okay. Then the second thing is path attribute. Okay. The characteristics of the advertised path. So what is the AS number, where it is originated, what is the local preference, type, length, value, all those things will be there. Together with that, NLRI information will be there, network layer reachability information. So all the list of IP prefixes and together with the prefix length that can be reached via the advertised path, that will be provided as the third value. So three informations will be part of the update message. So for one, if I'm sending only one update, that is for the one update message, one path only. So if multiple paths are to be updated, in that case, multiple messages to be sent. Fine. Now we'll see PGP notification message. So PGP notification message, when the notification will be sent, just now we have discussed, right? So when the notification will be sent, ma, we have four messages. Open, keep alive, update, and notification. When notification will be sent? Ma, when notification message will be sent? Students, I'm asking you when the notification messages will be sent. So if this is the case, you're doing for the all the contact sessions, then how will you appear for the mid-semester examination? It is a closed book examination. How do you prepare? How do you appear without knowing nothing? At last, multiple times I've told you. What is the purpose of open message? To establish a connection, keep alive, to confirm to maintain the connection, update only for sharing the update of the path, one update, we'll be having one path. If multiple paths has to be updated, in that case, multiple update messages has to be sent. Notification, it is for the error. When there is when the PGP router is detecting any error, in that case, uh, the notification and error message will be sent. Okay. So the router, whenever it gets the notification message, the router will be closing that particular PGP connection. Okay. So the notification message will have three information. First one is error code. Okay, so what is the category of error will be placed inside the error code. A part of a error code will be explaining the category of the error. Okay, and error subcode will provide the more information, the detailed information about the error and the data related to the error. So additional information related to the error to help in troubleshooting. So we have three informations that is a part of a notification message. Now we'll see PGP neighbor states. So PGP operates on the finite state machine. Okay, so the transitions will be there through a sequence of defined states like TCP. Okay, it forms a session with a neighbor. A finite state machine transitions will be maintained to form a session with the neighbor. Okay, it starts with the idle state. Idle state is nothing but the PGP process starts. So the router is waiting for the start event. Okay, so that is the idle state for starting the TCP connection to the neighbor, or else it will listen to an incoming TCP connection. Okay, the next one is connect. The TCP connection to the neighbor will be initiated. Okay, so if the connection succeeds, it will move to the next one. Fine. The third one is active. Active, the router is actively trying to establish a TCP connection with the neighbor. So if the TCP connection succeeds, it moves to the next step, that is the open. Okay. So open, the TCP connection is established. The router is sending an open message to the neighbor. Okay. So it will be waiting for an open message in return. So the received, uh, if also if the source will be sending the open message. If it also receives the open message, okay, if the path parameters matches, it moves to the next message that is open confirm. Okay, so open message exchange will be complete by confirming, by getting a confirm message. Okay, so then it will the router will be waiting for a keep alive message from the neighbor. So if the keep alive is received within the whole time, it moves to the established state. So or else if error, if in case error, it will be sending a notification and then it goes to the idle state. Okay, so this is how the transitions will happen. Fine. Now, we need to understand when to use PGP. So the PGP is best used only when the network administrator, if they understand the networks completely. Why? Because the PGP can be very complex and also it will be resource intensive. In the sense, it will not, it will be appropriate when at least one of the conditions they provided certain three conditions. So I can use the PGP if any of these conditions satisfies, or at least one condition satisfies. The first one is transit autonomous system. So you have an autonomous system. Your autonomous system, if it allows traffic to pass through to reach the other autonomous system, in that case, we can use a PGP. So commons for ISP, Internet Service Providers, and also the backbone providers where two autonomous systems, they want to exchange the edge router will be there. They want to, this is autonomous system number one, autonomous system number two. They want to share the information between two autonomous systems. Then in that case, we can go for PGP. That is the first case. So in if multiple external connections, your autonomous systems you have multiple links to different external autonomous systems. Okay, that is multi-homing. Okay, so in that case you can go for PGP. Fine. So not even one. If you want to have multiple autonomous systems connected, you can go for PGP. And also the third one, you need certain advanced routing policies. So manipulate the routing policy, and also you want to have a path selection for traffic entering or leaving the autonomous systems. Okay, so if you're preferring one ISP over another for outbound traffic, and if you want to control the inbound traffic paths, so in that case, the routing policies, you can give the routing policies and you can go for PGP. Okay, so if your network has only one connection to the internet, there is no need of complex routing policy, no need of PGP. Starting routing or default routing is well and good. That is enough. So when to use PGP? So if you want to connect to multiple systems, so multiple packets transit through, you have to reach to multiple autonomous systems, or even you have multi-homing where you have to connect to multiple autonomous systems, or you have to go with advanced routing policies. In that case, you can go for PGP. When not to use PGP? So when you're not supposed to use PGP, in the sense when you want to avoid deploying the PGP, uh, uh, in the sense you have a single internet connection. Just now I've told you, single internet connection or the AS connection. You have only one link to the internet, or you have only one link to the other another autonomous systems. In that case, you can go for a static routing, or a default route is more. It is simple and it will be more efficient. That's it. That is the first case. Okay. The second one, insufficient hardware resources. If you have lack of memory or lack of processor power on the edge routers, that is insufficient hardware resources. The edge routers, they don't have memory, they don't have power. Okay, in order to make PGP updates or store a large routing table. In that case, you should avoid PGP. Okay, you're not supposed to use PGP. And the third condition, in the sense, you have limited PGP knowledge. Okay, you don't have a strong understanding of route filtering, PGP path selection. It can lead to misconfigurations. Okay, which in turn lead to routing issues, or global route leaks will happen. Okay, so in that case, you have to avoid PGP, right? And the fourth one, matching ISP routing policy. Uh, so if you yeah, routing policy, if it is identical, uh, in that case, I don't want to have an additional control. Okay, or an additional benefit is not there. So if the in that case, you have to avoid the PGP. Okay, so if the routing policy is same for entire thing, okay, it is identical for all the internet service providers policies. In that case, why have to go for a PGP? It is same, fine. So in that case, you have to avoid PGP. Fine. So when to use PGP? PGP can be used in three ways. You can use PGP on three cases. The first case, when you have transfers to multiple autonomous, when you want to transfer the packets, when it transfers to additional or other autonomous systems, in that case, you can go for PGP. Or else, if you want to connect to multiple autonomous systems, you can go for PGP. And the third case, uh, you want to have a strict advanced routing policy. In that case, you can go for PGP. So when you have to avoid using PGP, the first one, if there is a single connection to either to the internet or autonomous systems, you're not supposed to use PGP. When you have an edge routers are running out of the memory or processing power, or multiple updates cannot be done. It can't store a large routing table. You have to avoid PGP. Okay, and you don't have an strong understanding on PGP. You have to avoid. It leads to misconfiguration. Okay, routing issues will happen. And the fourth thing, if the routing policy is identical for all the ISPs, in that case also you have to avoid PGP. Fine. Any doubts? Any doubts, ma? Now we'll see implementing basic PGPs, basic PGP, that is neighbor relationship. Now we'll start with neighbor relationships. Neighbor relationship, the scalability limitations. Why? Because we have 48, uh, the internet is connected and it will have more than 48,000 autonomous systems. Okay. And not only 48,000, 48,000 plus autonomous systems. That is, countless routers will be there. There will not be a single router which will be directly communicating with all others. Okay, that is the main thing that you have to understand. And all these neighbors, the PGP router will establish a direct neighbor relationship with only a limited number of PGP routers. Okay, so only through those neighbors it will be learning the path so that it can reach to the advertised networks with the help of a network. Okay, so there will be two things, PGP speaker and PGP peer, right? So PGP speaker, who's a PGP speaker? The uh, router which is running a PGP is called as a PGP speaker. Who's the PGP peer? Two neighbors, two routers, they want to connect to each other. Okay. So two PGP speakers, they want to directly exchange the routing information with each other. They are called as PGP peers or PGP neighbors. Okay. So what is the purpose of neighboring relationship? So they can directly exchange the PGP routing updates. Okay. So they'll try to provide a, or they'll try to build a network wide view of paths. Okay, with the help of multiple autonomous systems, without needing every router to connect to everyone, they'll be forming a network. That is the purpose of, actually the purpose of neighbor relationships. Okay, this is the example where PGP peers can be either internal or external to the autonomous systems. Fine. So internal PGP, we'll be using IPGP. They are called as IPGP peers. External, we'll be saying EPGP. Okay, so IPGP, it will be formed within the same autonomous systems. So see it, R2, R4, R3, they belong to the same autonomous system. They are neighbors. Okay, so they are under the same autonomous systems which are numbered as 65500. They'll be using IPGP. Okay, they'll be using, they used to share the routes learned from the external peers across the autonomous systems. Okay, the next one is external PGP peers. External PGP peers between the routers in different networks. So R3 and R1, they want to communicate. They'll be communicating with the help of EGPP peer relationship. Okay, 65500 and 65000. These two autonomous systems. A system in this autonomous system wants to share some information to a system in this autonomous system that can be made between EPGP with the help of a router R3 and R1. Okay, so R2, R1, they'll not be directly connected. They are not the direct PGP neighbors. Okay, so I can reach from R2, I can reach R1, right? So even though they can reach each other through the intermediate routers, they are not considered as neighbors. So PGP only exchanging the routes between the explicitly configured neighbors. So in this case, R3 and R1 are neighbors. So R2, R4 is a neighbor of R2. R4, it is a neighbor of R2 as well as R3. Fine. Now we'll see external PGP. So who are the external PGP neighbors? So the PGP sessions will be formed between the routers on the different autonomous systems. What is the purpose of doing that? To exchange the routing informations, right? So each PGP neighbors in this example, you have R3, R5, R4, R6. R4 and R6, they want to exchange the information between these two systems. R3 and R5, they want to share the information between these two autonomous systems. Okay, so they'll be running EPGP. So autonomous system relationships, AS relationship, they, if they run on different autonomous systems, if they want to exchange the routing information, information, then that can be done with the help of ePGP connection. Okay. So in this case, the TTL always it will be equal to 1. Why? Because they are neighbors. Okay. Already I've told you R2 can be, you can reach R2 via R4. R2 cannot be a neighbor of R6. Or R, R2 can be a neighbor of R4, not R6. But you can reach R2 via R4, but it will not be considered as a neighbor. So that's the reason TTL will be set to 1. Okay, directly connected uh, routers will be considered to be a neighbor. That's the reason the TTL will be 1. Right? So for exchanging the informations, the routing scope will be interdomain routing for ePGP, and intradomain routing will be using IPGP. Now we'll see external PGP neighbors. So external PGP neighbors, they'll be using ePGP, right? So external neighbor relationships, they're called as ePGP neighboring ship. Okay, so with they have certain requirements. So the first requirement is that different autonomous system numbers, they need different autonomous system numbers. So ePGP neighbors must be of different autonomous systems. Okay. So in the previous example, 65500, 65000, they have different autonomous system numbers, right? And what is the neighbor definition? So you have to configure the PGP neighbor command to define the remote peer. Okay, you have to manually do that. This will be telling the PGP who to talk to. Okay, and also the reachability. So reachability, the IP address specified in the neighbor command must be reachable at the IP layer. Okay, so ePGP neighbors, they'll be directly connected. So if they are not directly connected, you must use the ePGP multi-hop command. Okay. So this is the example of internal PGP neighbors. Internal PGP neighbors, in the sense we'll be using IPGP, right? So IPGP neighbor relationship. It is also called as IPGP neighboring ship. Okay. So that is within the same autonomous system, right? So R1, R2, R4, R3, they are within the autonomous system 65500. They can use IPGP. They can form IPGP session. Okay, so the neighbor command must be used to specify the remote peer. They have to do it manually. So PGP does not automatically discover the IPGP neighbors. Manually, we have to do it. Okay, so TCP connection can be established with the help of TCP port number 179. Okay, this will be forming the session before exchanging the routing informations, right? And the IP address will be given in the neighbor command. So it can be reachable via IPGP before PGP can form a session. So IPGP neighbors, they does not require to be connected directly. Whereas in ePGP, EGP does that. So that's the reason TTL will be equal to 1. So full mesh requirement will be there. So by default, all the IPGP routers within the autonomous systems will be in the full mesh configuration. One router will be connected to all the routers. So this will be optimized with the help of route reflectors. Right? Now we'll see internal PGP. Again, we'll continue the requirements. Several requirements are there. So it should be within the same autonomous system number. Likewise, in requirement of external PGP, they should need a different autonomous system. But here they need a same autonomous system numbers. Okay. So who are the neighbors? Neighbors, we have to configure the neighbors manually with the help of neighbor command. The PGP does. Why? Because the PGP will not discover the neighbors automatically, either the external or internal PGP, right? So the TCP connection must be established before exchanging the routing updates. So what is the purpose of reachability? Reachability must be IP reachable. Okay. So before the session is confirmed, IP reachable. It should be IP reachable. Okay. So it should be providing the reachability. Fine. So this is an example how IPGP in a transit autonomous system works. Okay, so autonomous systems that sits between two or more autonomous systems and how they are passing the traffic. In this example, we'll see. So we'll start from 65102. This is the autonomous system. This is actually the transit autonomous system between 65101 and 65103. So traffic between R1 and also R6 must pass through this particular autonomous system. Okay, so we'll be using ePGP. From R1 to R2, we'll be using ePGP, right? So this is between autonomous system number 65101 and 65102, right? And also from R5 to R6, we'll be using ePGP. So ePGP, they need a different autonomous system number, right? So in between R2 and R5, it is within the same autonomous number. So in this case, we have to use IPGP. So even it is not connected, it is a fully mesh connected topology will be provided. So all the routers will be connected to all other routers. Okay. So R2 to R5 within this particular autonomous system will be carrying the routes which are being learned from R1 as well as R6. Okay. And also vice versa. From R1, what are the networks connected? R6, what are the networks connected? Okay, so it will be using running OSPF inside the autonomous system number 65102 in order to provide the reachability between all the routers. Okay, R2, R3, R4, and R5. So not all the routers in the autonomous system, they'll be running the PGP. Only in this case, R3 and R4 will run OSPF. Okay, so these two things will be running OSPF and PGP. Why? Because it should connect to the external network. So for external network, it should run PGP, right? So these two routers, they need not to use PGP. Why? Because they are connected internally. No other external systems, autonomous systems are connected here. So they don't need PGP connection. Fine. Now we'll see what is a transit autonomous system. So transit autonomous system, it is actually an autonomous system which helps in forwarding the traffic from one external autonomous systems to the another external autonomous systems. The previous example itself we have seen 65102 is a transit autonomous system. So the traffic will flow from autonomous system number 65101 to 65103 with the help of 65102. Okay, so they can be if I take ISP, it's a simple example for the transit. Okay, so internet service provider. So all the routers in the transit autonomous system, they need to know the complete knowledge of the external routes, right? So that only they can able to forward the traffic correctly. Okay, so for that we have to redistribute the PGP into IGP, IGP, which runs on the edge routers. Okay, so not recommended, but the internal routing table will be very large. So it will have hundreds of thousands of routes. So for that, we can go for IGP. So IGP like OSPF, IACIS can be running on the edge routers. Okay. So they'll be designed to handle the scalability. Fine. So there is this type of approaching can even cause high CPU memory usage, low convergence. Okay, so that's the reason we'll be running IPGP on all the routers, okay, in the autonomous system. So we can scale much better. Fine. So IGP, it is not scalable. In this case, R3 and R4, it is not running the PGP, right? It is running OSPF. Scalability issues will happen. So in order to avoid that, we can even make R3 and R4 to run the PGP. Fine. So we can limit the scalability problems. It scales much better, and also it will be keeping full PGP path attributes. So it allows all the routers to learn about the external routers, external networks. Fine. That is the advantage. And what is non-transit autonomous system? So non-transit autonomous system, it is actually an autonomous system which will not carry any traffic between two different external autonomous systems. Okay. So if the organization, if it is having multiple autonomous systems connected, in that case, it is not called as a transit. Instead, it will be called as a multi-home. So I have three autonomous systems. Okay. So these are the edge routers which are connecting these three autonomous systems. AS1, AS2, AS3. Okay. So in this case, AS2, it is not called as transit. Why? Because the transit will carry the information from one autonomous system and it will pass to another autonomous system. Okay. So different organizations from one organization to another organization. But here, all the autonomous systems are part of a single organization. So it is called as multi-homed autonomous. It is actually a multi-home network. Okay. So in this case, we'll not consider even as ISP provider. So all the three autonomous systems cover the same ISP provider. Okay. Are part of the same ISP provider. In this case, we cannot say it is a transit network. Okay. So even though it is not a transit network, but all the routers within the autonomous system need to know all the PGP routes which are being advertised by other autonomous systems. So they can make the accurate routing decisions, right? So instead of going for an IGP, IGP will be flooding the route. Okay, so in that case, we can go for PGP. So PGP does not automatically flood the routes. Periodically, it will be updating. It will be advantage. Okay, so PGP was designed so that not all the routers in autonomous systems will be running the PGP, right? So the protocols, they have to allow IPGP speakers to exchange the routes with each other. So it will prevent the routing loops from forming inside the autonomous systems as well, right? Now we'll see TCP and full mesh network. So PGP will be using TCP. Okay. So TCP is a transport protocol which works for PGP. PGP will run on the top of the TCP on the port number 179. So TCP sessions cannot use broadcast or multicast. They have to use only unicast between two endpoints, right? Likewise, PGP also cannot use broadcast or multicast. That's the reason updates, even the update can be given for only one path. So if there is multiple updates, multiple parts need to be updated, multiple updates messages has to be shared. But only it is a unicast message, not the multicast message, right? So whatever the routes learned from an IPGP peer, it cannot be advertised to another IPGP peer. Okay, so this rule will prevent the routing loops inside the autonomous systems. Okay, and also they need a full mesh network. So full mesh network in the sense uh, lack of broadcast and multicast will happen, right? So each IPGP router must form a TCP session, fine? So with every other router in the network autonomous system. So this can be done using the neighbor command with the help of a PGP configuration. Okay, so all these things will be connected. So this will arrange a full mesh IPGP. So when a PGP router receives an update from an external autonomous system, it will be sending the update to all the PGP networks, all the IPGP neighbors. So all the neighbors will receive the update. They do not send it to other IPGP peers, but they'll receive the messages from the edge router. Fine. So this is the one which shows three autonomous systems. Autonomous systems which are numbered as 101, 102, and 103. Okay. So 101, the edge router is R1, 103 edge router is R6. For 102, you have two edge routers, R2 connected to autonomous system 101 and R5 connected to autonomous system 106. Fine. So it uses ePGP and the routers within the autonomous system, they use IPGP. Okay, so OSPF will even OSPF is also running within the autonomous systems for internal routing. It lacks with scalability issues. That's why PGP is also made to run on these two internal routers. Okay, there is no need of running, but scalability issues will happen. That's the reason it is also running PGP. Okay, so what is the purpose of ePGP? ePGP, it runs between the routers in different autonomous systems. iPGP will be running between the routers in the same autonomous systems. Okay, what is the PGP rule? In IPGP, the router, uh, whatever the router learned from one IPGP neighbor, it will not be advertised to another IPGP neighbor. Okay, unless it is a full mesh. So here, no IPGP update will be happen. So if all these things, see here, if it is in a full network, the update will be given to all the neighbors. Okay, so R2 now it is connected to R4, R3, R5 and also to R1. So whatever the updates comes from R1, it will be sent to R4, R3 and R5. Right? Now we'll see the configuration requirements. So before configuring PGP, you must need to collect certain details. So what is the autonomous number? Okay. So what is the autonomous number of the remote autonomous systems as well, together with the IP address of the neighbors, that is the peers. Okay. So IP address of the routers, you will you wish to establish a connection. The third thing that you have to collect is networks. What are the networks you have to advertise into PGP? Okay, so the networks from your routing table that should be announced to PGP neighbors. So for that you need to maintain the basic PGP configurations. Three steps are there. First step, you have to define the PGP process. So you should enable PGP on your router by specifying the corresponding autonomous number. So if I'm using Cisco, I'll specify router uses PGP and the autonomous system number 65101. And the next one, you have to establish the neighboring relationship. Okay, so you have to specify the neighbor's IP address and also the autonomous system to form the peer relationship. So I'll be using the neighbor command. Neighbor, who is my neighbor? The 32-bit IP address will be provided here. Okay, remote autonomous system, the neighbor autonomous system number, that is AS65102. Fine. So the next one, third thing, you have to advertise the network into the PGP. So you have to use the network command. So network command, network. So what is the network address? 192.168.10.0 is my network address. And what is the mask? Subnet mask you have to provide here. Fine. So this is how we have to follow the three steps in order to have the basic PGP configuration. So router, neighbor, and network. Three commands are required. Fine. Now we'll see the PGP configuration mode. So what is the command to enter the PGP configuration mode? So for that, we have to use router PGP autonomous system number. Just now I've told you it is a global configuration command, which is used to specify the local autonomous system number to which the router it belongs to. Fine. The next, what is the purpose of specifying the autonomous number? The PGP must know the router's own autonomous system number. So with that only, whether a configured neighbor, it is an IGP peer, whether it is belonging to the same autonomous number or different autonomous system, it can be identified when it is configured with the autonomous number. Okay. So if the autonomous number is not provided, then we have to explicitly specify you have to use IPGP. This is not having the same autonomous number. So this is you have to use ePGP. Okay, so in order to avoid that, you need to specify the autonomous number. Okay, so the router can run only one PGP process at a time. Okay, so if the router is configured with, say for example, router PGP autonomous system number 65, that is 65000. I've configured. Okay, so later I'm changing it as PGP 65100. So the router will display, in this case, the router will definitely will display an error. Okay, so it will say it is already configured with 65000, but you're trying to reconfigure with 65100. Okay, that mismatch will happen. So how to define the BGP neighbors? Fine. So the neighbors can be defined with the help of neighbor command. Neighbor, IP address, remote as autonomous system number. Okay. So this way you can activate the PGP session. Okay. So IP address will define the router's IP address. Okay. So example, router PGP 65000. Then I can provide the neighbor for this, providing the IP address 168.10.2, remote as 6510, 65100. Okay, so this is the local autonomous number, and this is the neighboring autonomous. So the local is 65000, and the local neighbor is 65100. Right? If you want to provide some other neighbor on different IP address, I'll take 192.168.20.2. This is the IP address of another router, 65200. Okay, two neighbors are there. So 65000. This is one autonomous system running on two routers, R1 and R2. Okay, so you have different autonomous system here, that is 65100, and here you have 65200. Here also you have one router. This is R3 and this is R4. Okay. So here R4 address I've given, R1 address, the router's IP address is given, and the uh, autonomous system number is given. Likewise, the router's IP address and autonomous system number is given as the neighbor. Okay. So here 192.168.10.2. Here it will be 190.168.20. Fine. Any doubts, ma? Do you have any doubts? Any doubts? Only response. One response all the time. Can I please to check it out whether your the assignment is the quiz is enabled? Yes. Fine. Complete the quiz then. So now please don't leave the meeting. Complete the quiz. Post the status in the chat box and then you can leave. Come on, don't leave the meeting. Done. Okay. Thank you, ma'am. You have completed. You can leave the meeting. Thank you, ma'am. Others, please complete. Students, make sure you complete the quiz. Fine. I'll end the meeting. Make sure you complete the quiz. Fine. Thank you, ma'am.